All right, and we're back, everybody. No, tomorrow is a good day. Tomorrow you learn something really cool. But for real. But for real.
I really can't. Well, you just said that we were going to.
But for real. But this is really cool, though, too. This 3x3 system. Now, what did I say about determinants? You can only have a determinant of a what kind of matrix? Square matrix, right? Square matrices are the only ones that you can find the determinant of. So yesterday we talked about a 2x2 matrix, and it's really easy to find the determinant of a 2x2. You just take the main diagonal, the product of the main diagonal minus the product of the secondary diagonal, the other diagonal, right? And then that was it. For a 3x3, it's a little bit more involved. So let's take a look here. Now, go with me here. Just watch for a second. Just look up here for a minute. Because I'm going to try to explain it as we go, and I think once you kind of do it once or twice, you'll get the hang of it. Because again, it's not a difficult thinking process. It's like, okay, once you set it up, it's really just trying to do everything without error, without writing down a wrong number here or there. Okay, so what you're going to do is you're going to find the determinant of a 3x3. Basically, finding the determinant, everything needs to be multiplied with everything. Every diagonal needs to be multiplied with every other diagonal. Okay? And then we need to subtract away all of the other diagonals. So here's what I need here. I need to have A1, B2, C3, B1, C2, and A3. Every entry needs to go with each other. And C1, A2, B3. That means that every A1 went with every B value, A2 went with every B and C value, A3 went with every B or C value. Okay, now, here's how we make that happen. We rewrite the first two columns out of our matrix on the right side of the determinant. Okay, so we just copy paste, Control C, Control V. Now, we multiply the diagonals still. That process did not change. But here are my main diagonals now. Okay, I have three main diagonals. Okay, I have three main diagonals. What I do here is I take the sum of all of those diagonals together. So I multiply this, I multiply this, and I multiply this, and then I add those things together. Remember, the determinant is the main diagonal minus the secondary diagonal, the other diagonal. Same process is here as well. I have the main diagonal minus this, this, and this. Okay, so you're almost going to make like a lattice pattern here, where I'm crossing each one of them, right? So I have main diagonals multiplied together and find the sum, and then I have the secondary diagonals multiplied together, then find the sum, and in the end, I find the difference between those two values. That's how to find the determinant of a 3x3. Let's practice. Let's try it here. So the first thing that we have to do is rewrite the first two columns of my matrix over again. Okay, so I'm going to say 4, -3, 2, -2, 10, 6. You just rewrite them, copy paste on the right side of the matrix. And now, I like to use highlighters here, so I'll keep doing that. I'm going to highlight all the main diagonals. Let's do that operation now. Okay, so I say 4 times 10 times -1, -40. 2 times 1 times 2, -4. 0 times 3, 0 times anything is 0. And then I'm going to subtract away all of the secondary diagonals. Again, I got those three numbers from the three highlighted diagonals, three yellow highlighted diagonals. 4 times 10 times -1 is -40. -2 times 1 times 2 is -4. 0 times negative 3 times 6 is 0. Okay, so now I do the secondary diagonal. I go from bottom to top. Here, here, and here. Okay, so now that means that I'm going to subtract away the sum of 2 times 10 times 0, okay, 0. 6 times 1 times 4, 24. Negative 1 times negative 3 times negative 2. Okay, negative 1 times negative 3 is positive 3. Positive 3 times negative 2 is a negative 6. And now we add these things together. Okay, so I've got negative 44 minus, and then I've got 24 minus 6 is 18. Negative 44 minus 18. So my determinant of this 3 by 3 is negative 62. Make sense? Again, the process is not difficult, just the setup is difficult. I got one from Sherry. She had an extra one.
Okay.
Thank you. Questions about that? Now, here's the fun part. Remember Kramer's rule for a 2 by 2? Remember the process of finding each value? How you find the coefficient matrix determinant? Then, to find the x value, to find the y value, you just replace the constants with the coefficients. That's fine. And divide by capital D. The same thing is true for a 3 by 3. Okay, the same thing is true for a 3 by 3. Now, do you guys remember solving for 3 by 3 systems? Right? Remember where we had to do that whole process where we eliminated one of the variables in 2 different equations, and then we created a 2 by 2 system, and then we had to use substitutional elimination to find that value, then plug it in, to find the y, and plug it in, and find the z. That whole process, this is an alternative to that. I'm not saying this is quicker. I'm not saying this is easier. I'm just saying this is an alternative. All right, so take a look at what we have here. I've got a 3 by 3 system all set up in what's called standard form again. Ax, by, cz is equal to d. And now d is our constants on the right side. Okay, they're all set up. X, y, z, constant. Now, to find our d, again, capital D, I need to use that coefficient matrix and find the determinant of that. As long as the determinant is non-zero, nothing weird is going to happen. Take my word for it, none of them are going to come out to be 0 in this case. If they come out to be 0, we might have an inconsistent or a consistent system, an infinite solutions or no solutions. It just kind of depends. We won't touch that for right now. All right, so how do you find your x value? Well, the rule was remove your x coefficients and plug in your constants. Same thing. Remove the x coefficients, a1, a2, a3 goes bye-bye. Inputs, d1, d2, d3. Find the determinant, divide by big D. The y value, remove the y coefficients. Plug in your determinant, or plug in your constants. Find the determinant, divide by big D. To find the z value, remove the c's, the z coefficients, plug in your constants, find the determinant, divide by big D. Again, what's great about this in contrast to the algebraic solution to the 3 by 3 system is that, remember, if you got your first variable wrong, or if you screwed up one of the equations in the algebraic solution to the 3 by 3, all of your variables were wrong, right? Didn't matter how you found them, what order you, all of them were wrong if you missed the first one. These are independent from one another, just like they were in a 2 by 2. The only thing you have to be very careful is creating your capital D. All right, so let's solve this. Let's do this one. First thing I need to do is solve for capital D. Okay, solve for capital D. I'm going to make this just a little smaller than that. Okay, so capital D is going to be our coefficient matrix determinant. Okay, so we've got, I didn't even look at it, but this is set up correctly, right? xy constant, or sorry, xyz constant, yep. So I've got a -1, a 2, a 3, a 1, a 3, -4, 2, 1, 1. I was just about to check to make sure they were all correct. -1, 2, -3, 1, 3, -4, 2, 1, 1. Okay, we're good. Now, copy paste our first two columns and start finding your determinant. No. Okay, so that's going to get me -1 times 3 times 1. Okay, so that's -3. 1 times 1 times -3. Okay, plus another -3. 2 times 2 times -4. -16. Everybody follow me there? I'm just going to double check that. -1 times 3 is -3. 1 times 1 times -3 is -3. 2 times 2 is 4. 4 times -4 is -16. All right, now I do my secondary diagonals. Sound effects help, really. I've got -3 times 3 times 2. Okay, -3 times 3 is -9. -9 times 2 is a -18. -4 times 1 times -1. +4. 1 times 2 times 1, 2. Okay, so now I'm going to say that's equivalent to, all right, so I've got -3 plus -3 plus -16. So that'd be -22, correct? -22 minus, and then we've got -18 plus 4 plus 2. So -12. Correct? Add together. Well, I know I'm going to add because it's minus a negative, but that gets us a -10. Okay, so that's capital D. That's our capital D determinant. So let's find our x value. Well, the x value I know is going to be divided by -10. But how do we create the numerator determinant? Well, it's going to be remove the x coefficients, and in place I write 7, 1, 4. The other ones remain 1, 3, -4, 2, 1, 1. And then we start that process all over again. 7, 1, 4, 1, 3, -4. I'll get my highlight, break out the highlighter. Wah, 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 wah. I'll do the other diagonals while I'm highlighting. Okay, so that's going to give me, okay, so something divided by -10, right? Okay, 21, 4, -8, minus 24, -28, and 1. Okay, so I've got 25 minus 8, so 17, minus, and then I've got -4 plus 1, -3. Oh, and look at that. That's going to give me 20 divided by -10, -2. So the x-coordinate is -2. Now let's find the y value. So the y value is going to be, okay, I'm going to keep my x's now, -1 to -3. The y coordinates get replaced with the 7, 1, 4. And the z stay the same, 2, 1, 1. All divided by -10. And then we start that process all over again. Copy paste, -1, 2, -3, 7, 1, 4. Highlight. Wah, 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 wah. Okay, so that gets me -1 plus -21 plus 16 minus -6, -4, +14, all divided by -10. Okay, let's see what we get here. That's -22 plus 16 would be -6 minus, this would be -10 plus 14, +4. Oh, cool. -6 minus 4 is -10. Divided by -10, +1. I'm two-thirds of the way there. I'm excited. We're rolling here. Z is equal to something divided by -10. All right, and then we replace, so we got -1, 2, 3. The 7, 1, 4 goes in for the y values. Next, jump back up here. 1, 3, -4. Why do I keep forgetting that -3? 1, 3, -4. So my y values get are the same. My z values get replaced by the 7, 1, 4. All right, so now copy paste. Oh, I used the same color. Come on now. I even selected blue. Oh, for real. Those went away. All those sound effects for nothing. Okay. What does that feel like I'm teaching to myself, people? Yeah, thank you. We could have been playing wiffle ball this entire time. -12. It's going to be a lot longer. -12. -3. Ooh, 7 times 2 times 4. -4. Is it -56? -56. That's a big number. 14 times 4 or 8 times 7, yeah. -56. Subtract away the blues. Ooh, that's a big one too. 9 times 7 is 63, so -63. And then we got +4 and +8. Okay, so that means I've got negative, I'm going to have to do this one later. -12 plus -3 plus -56. -71. Oops, sorry, not plus, minus. And then 12 would be -63 plus 12, so -51. Which makes sense, because -71 plus 51 is -20 divided by -10 is 2. So we get -2, 1, 2. I mean, I don't know. I think that might take more time than the algebraic one, but I'm just cool. It's cool. Like who came up with this? Like this is the funniest part about this to me. It's like, who was sitting there saying like, I think I know what to do. Let's copy down those 2 next columns right over again. And let's just start multiplying diagonals all over the place. Like, who came up with this junk? I should look at that book and see who actually came up with it. I mean, I can only assume it's Kramer.
You just find X and Y and just substitute.
But if you got X or Y wrong, then you would get 0. See, it's all independent, so you gotta solve them all in their separate ways. You know what I mean? That's the joy, that's the beauty of Kramer's rule, is that they're all independent. See that? Jog it off. Just jog it off. There you go. You don't have to do, you don't have to do all of them. You do have to do both sides. It's 2 to 10 even, and then number 13. I'm so funny. 2 to 10 even, and then number 13. So you're going to do 1 3 by 3 determinant up top in number 2. 4, 6, and 8 are 2 by 2s with Kramer's rule. 10 is the only one, only 3 by 3 that you'll have to use Kramer's rule on. And then number 13 is a word problem where you have to create your system and then solve the 2 by 2. You do not have to do number 12. It's 2 to 10 even, and then pick up number 13. Well, I'm still recording. Shout out everybody at home. Wish you were here. We got an exciting mood in the classroom today. Jennings is just busting out of his chair. He's just so excited to be here. All right, see you, everybody.